All right. Welcome back. So we've been kind of working our way through threads and now have to start really talking about synchronization for real. So that's going to be our topic for today. If you remember briefly last time, we talked a little bit about cartoon sketches like this that showed, for instance, how threads are started. If you remember, this particular sketch looks at the fact that we sort of grow the stack down here until we hit yield. That calls run new thread, which calls switch, and switch ends up altering the stack pointer and so on. And so if we switched to some other thread that was already running, we'd have a stack that looked like this and return our way back up. On the other hand, if we want to start new threads, we just create a stub that we can return into, and in the act of returning into, it starts executing the thread. And so this is very similar to what happens in most schedulers. I wanted to see briefly if there were any questions on that, and then I want to dive into synchronization, because that's going to be our main topic for today. And by the way, that at the very end of the lecture, or near the very end of the lecture, we did talk through kind of the way that interrupts are handled, and timer interrupts in particular are handled in PNTOS. And that sketch that's in the slides is actually a pretty good example of how that all works. And for instance, how an interrupt can look exactly like this as well and end up calling switch eventually and switching to another thread. So, all right, so today I actually want to talk about synchronization in detail, and hopefully we're going to talk a lot about locks. That's going to be our main topic. Hopefully we'll get to actually talk a bit about semaphores, and maybe we'll talk about monitors and condition variables, not entirely sure. And throughout this, what we're going to try to develop is an overall way to approach parallel programming. And to do that, I wanted to put up, this is a chunk from my favorite Dilbert cartoon ever. It was in a Saturday paper, which is why it's in color. And everybody's sitting around the table, and the pointy-haired boss starts out and asks somebody at the table, well, can you tell me about your project? And he says, my project is a whole new paradigm. And of course, everybody's like, paradigm? What's paradigm? And he's like, well, as in paradigmism, my project's a whole new paradigm. But enough about my project. What about yours? And everybody's like, well, my project's a whole new paradigm as well. And they kind of go around the table. But basically, paradigm means pattern. And one of the ways to approach programming in parallel is to develop a set of patterns that are known to be good patterns, and that's going to be our approach here. So we started really diving down here, and the question is really, if you can schedule in any possible way, can you test for correctness? And the answer is mostly no. Okay, and so you really shouldn't assume that testing is going to find out whether your parallel program works or not. That's just not the right way to do it. There are some maybe slight advantages. So we talked about independent threads briefly, and we said, well, what's an independent thread? Well, two threads are independent if they don't share any state. And the good thing is then maybe the execution is deterministic, because the execution of an independent thread doesn't depend in any way on the scheduler. The worst that happens if somebody schedules on top of you and you're an independent thread is you run slower. Okay, and oh, isn't this great? I can run the same thread over and over again to debug it. It's reproducible. And, it doesn't matter which scheduler you're running. Now, you get to actually develop a couple of schedulers for Project 1. And what this basically says is it doesn't really matter which scheduler you've got if you've got an independent thread, because you're not impacted by scheduling order. Of course, what's the point, pretty much, right? So if we have threads, maybe we want them to be cooperating in some way, and they're not going to be independent. And so now what's it cooperating? Well, there's some sort of shared state. There's a variable between them or something to that effect. Maybe they're cooperating together on a multi-core to do something in parallel, or maybe they're cooperating to do some user interaction. And of course, now suddenly things are non-deterministic because you got two threads. The ordering between them matters. Which one runs first? Do they run partially and then go on? And I'm going to give you lots of examples of this time. It's not reproducible. You can't just rerun the one thread. In fact, you can't just rerun the two threads. Okay? And non-deterministic and non-reproducible means non-fun, right? It means that bugs are intermittent. And of course, this was the Heisenberg idea. The closer you look, the more it changes. Right? And this is why it's very important to go after patterns of designing your programs rather than I'm going to design a bunch of stuff and hope it works. And then if it doesn't quite work, I'm going to test it a bunch of times and hope I find the bug. That's a really good way to tear your hair out. Okay? So interactions complicate debugging a lot. And, and unfortunately, you could ask, is any program truly independent? Well, no, because they're all sharing the operating system. And so underlying, there's often some state that goes on there. And there's an example that many of you have encountered that a buggy device driver causes thread A to crash thread B. And, what is the sharing there? Well, thread B was completely independent, but, they share the underlying operating system. There is a kind of a funny thing that you guys depend on. How many people ever considered the notion that a C compiler could be buggy? Okay, a couple of you. Well, it turns out if your compiler is buggy, and I've dealt with some projects where we were designing everything from scratch and even the compiler was buggy, you can imagine that trying to debug your program is challenging because, maybe it's not even your code that's wrong, it's the compiler. And there is an interesting case that we used to talk about a few years ago. It's been a while now, but where there was actually a C compiler that recognized whether you were trying to put debugging code in or not, and would compile it incorrectly unless you were debugging, in which case it compiled it correctly. And then, of course, your printfs all seem to work fine, and then you take them out and nothing works. Don't worry, that's probably not a common case for you. But it is true that putting in debugging statements can often change the behavior enough that you get different behavior. So you could put in printfs and suddenly things work. Has anybody ever been parallel programming and put in printfs and things then worked all of a sudden? Yeah. So the reason for that is maybe it runs a little more slowly as a result or something. The console output changes the timing. The other thing is you might put in debugging and it overruns the stack, and as a result of putting the debugging statements in, it's worse. Okay, isn't that fun? And so these errors are really hard to find, and they can often depend on things like the layout that the kernel chooses for your memory. Okay, question?
So there's nothing like GB that will say, we're going to force it to be the same as it would have been otherwise, and then you look at it?
So the real problem here is that there's this non-deterministic element in the middle there, which is the scheduler is deciding kind of what order to do things. And if you could, it's hard to get the scheduler to be exactly the same ordering. But if you're working in a simulated environment and your scheduler timer choices, sometimes you can arrange so that the timer maybe goes off at exactly the same places in the execution. It gets pretty hard to do because, you're simulating instructions that are running somewhere and the timer is this asynchronous thing, and so you have to figure out how to make it work exactly the same. So it is an interesting thought, and it's in principle, I guess, possible to have a debugger like that, but it's very hard. Yeah, question?
Sorry, what do you mean by debugging statements overrunning the stack?
So what I mean is you put in debugging, if you're debugging the kernel, printf is another procedure call, and if you're in the kernel, as you have started to find out, has a limited stack that it's working with. We have those 4K stacks. And so if you're debugging the kernel itself and you're down close to having your stack overrun and you put in a printf, now all of a sudden it's calling stuff and it overruns the stack and game over, basically. You're in trouble. So that one's less likely when you're in user mode because you have a lot more stack available to you. Now, by the way, this randomness can be good. So many of you have probably generated a key using randomness by typing on the keyboard, and it generates an RSA key for you or something. Anybody done that? Probably a few of you. So there are some cases where the randomness is good, but oftentimes it causes problems with debugging. So why cooperate at all? Okay, if cooperation's a problem, then never cooperate. Okay, this is the antisocial, go into a cabin in the mountains sort of view of programming, right? And of course, it's very useful. So, sharing resources is very useful. One computer, many users. One bank balance, many ATMs. Embedded systems, basically you have robot controlling all of the pieces together. There's so many uses for shared state that you just basically can't avoid it, okay? And that's just, it's basically just a pipe dream to think you couldn't. The other big advantage you get with multiple threads is speed up. So if you have multiple cores, because you have a multi-core processor, then you could have more than one thread, and now things go twice as fast on the right circumstances, okay? And then you can also get an advantage of modularity to having cooperating threads. Now, here's something that you've kind of been dealing with now in the last homeworks and so on, which is pipes. And we've talked a lot about pipes, where GCC, the compiler, for instance, might actually call a set of stages that are piped together, a C preprocessor, a couple of C compilation stages, an assembler, and a loader, and they're piped together. Why design it that way? Well, maybe it's more modular. By designing these pieces separately, not only do you get a little parallelism out of it, but you get modularity that might make it easier to debug under some circumstances because you could take the C preprocessor separate from the others. So bottom line, multiple threads are tricky to deal with, but you want to deal with them, and so that leads us to how do you synchronize? Okay? And synchronizing... what does synchronizing mean? I mean, what do I mean when I say, how do you synchronize? I mean, I've got the title of this lecture is Synchronization. What do I mean? Yeah. Get stuff to happen when you want it to happen. Okay. Can you be more specific? Yeah.
We're doing it right now.
Okay. We're not talking over each other, you mean? Yes. Okay, I'll buy that. Synchronizing means if there's a shared medium, like the air, which is what we're doing right here, we have to make sure that it gets used in a way that tends to give you the correct result rather than to obscure the result. And I'm going to show you lots of examples of that. But what's the obvious way to correct a synchronization problem? Yeah. Good. Timing. What else in particular? Lock. Okay. And ultimately, all those things do what? So what happens if you and I both start talking at the same time? What do we have to do to correct it?
Tell the other person to shut up.
Yeah. I suppose tell the other person to shut up. Or the other way to put this is waiting, right? So the key thing about synchronization is somebody waits so that something doesn't get scrambled. It's all about waiting. Okay, but it's about clever waiting. Okay, so let me give you a couple. Here's an example of a web server. So this is an example you've already seen, but the server has to handle many requests. And the non-cooperating version here, which you've already kind of seen, is that there's a loop, there's an accepting of a connection, and then we fork off something to handle the web server, right? That was our big example from a while back. And this seems nice because it's protected and it's got parallelism, but what are some disadvantages of doing this, forking off a process for every incoming request? Yeah.
Too many requests.
Okay, if you got too many requests, suddenly your blog is really popular. We used to call that slashdotting. You got a problem because you generated all these processes and the server falls over. What else? Yeah. I'm sorry, say that again?
If there's like more connections on the same computer, like the browser is opening separate connections, they all will then you're having separate.
Yeah, so you're kind of getting around this if you've got many connections. I think the right thing to say here is I'm not actually looking for something too complicated. Basically, constructing processes might be expensive. If you've got too many of them, it's a problem. We'll go with that, okay? And so maybe we could, and the other thing, by the way, is none of these processes can share state with each other. And so if you want to have an in-memory cache of some sort, you got to do a lot of inter-process communication just to make that work between the different connections going across the browser. And so what we might want to do is let's use one process and multiple threads. Okay, and so here's the threaded version, which is we accept a connection, we fork something else off. Okay. Now the advantage here is we've gone to the lower overhead thread model. We've lost a bit of our protection, but let's ignore that for a moment because it's all within the same server. And this is lower overhead and seems kind of less wasteful. And this looks almost the same, many advantages. And the only thing it doesn't do for us, though, is it doesn't help with denial of service attacks because it's still possible for many connections to be launched from all over the world and essentially take this guy down by having too many threads. Now, it's true that this server will be taken down less quickly by too many connections than the process one would because processes are more expensive. So this one is a little stronger, but what could we do that's better here if we wanted? If we're worried about too many connections taking the server down, what could we do with this? Yeah. Okay, we could limit the number of connections. Okay, good. And that will limit what?
So we might not be able to serve all the requests we get, but the requests we do get, we can guarantee some kind of service.
Okay, so basically what you're trying to limit here, though, is the total number of threads that are running, right? Okay. Now, it turns out we don't have to be quite as draconian as limiting the connections. What we can do is use something called a thread pool, which is, I'm sure you've all heard of this before, but I'm going to put it out anyway. So the idea is, no, we don't have unbounded threads. Instead, we have a container worth of threads. And we allocate a pool of workers, and we make sure that the number of threads actively running at any one time is limited. And we want to queue up all of our requests otherwise. And what's nice about that, of course, is that the listen socket does the queuing for us already. So the basic way to look at this is, this is not a brain, this is a pool of threads, okay? Is there's a master thread that's going to take connections and hand them off to the thread pool, and we might do something like this. The master allocates a well-defined set of threads, and it just keeps going through, and for every connection, it accepts it and then puts it on a queue, and does a wake-up process, and we're going to talk about wake-up when we get to more advanced monitor-type synchronization. But and then it just keeps looping, and so it takes every connection in and then just puts it on a queue without processing it. And what we have for every worker is each worker, and there are potentially many of them, basically says, well, is there something on the queue? Okay, dequeue it, process it. Otherwise, if I got back null, put myself to sleep until somebody wakes me up. And we just keep doing that. And so suppose we pull up 10 threads, then 10 threads are busy processing things. If we pull up 20 threads are processing things, but the total amount of parallelism here is fixed. Okay? Now, to make all of this work, of course, what have I introduced? A bunch of synchronization, because that master is putting things on the queue, the different threads are taking things off the queue, and they got to do it in a controlled way, or we're going to end up with a mess. Okay, because if you remember queues from 61B, they have multiple sort of memory operations involved in in-queuing and dequeuing, and so we're going to need to get this right. Okay? Everybody with me? Okay, but this is a great use of multiple threads to get both parallelism and do so in a controlled way. So, all right, so here's another version of this I'd like to talk about. So here's the ATM issue. So you've got sort of the bank server here, and every ATM needs to access the same set of bank accounts. And so the question is, so how can we do this without corrupting the database? Simple, right? And suppose that we want to handle requests from the ATM network. We could do this. The bank server says, well, get the next request, process the request, and it does this in a loop. Okay? And what does process request do? Well, it says here's what the operation is, here's the account, here's the amount. You know, if it's a deposit, do one thing. If it's an insertion, do the next thing. And seems reasonable. What's probably a little undesirable about this particular implementation of a bank? Yeah, it's serial. That's very annoying, right? ATM, which are actually kind of a dying breed. Everybody here used an ATM before, by the way. Maybe I'm going to have to start changing my examples. But you could imagine that if all of the folks in the United States that had Wells Fargo went through this code, we would have enough annoyed people out there that they'd drop Wells Fargo, right? Because there's just no parallelism in this. And so now the question is, how do we do the parallelism? And let's look at some interesting things here before we get to the parallelism. So what does deposit do? Deposit gets the account, adds some money to it, and stores the account back into the database. Okay, and now you can start to see what might be a problem here. What if two deposits are running at the same time? Right? Both of them get the account amount. Both of them update the balance. They both go to store the result back, and one of them gets written over by the other one. Right? Your parents deposit $100. You deposit 10. Lucky you only got 10 instead of 110. Okay? So this seems like a bad scenario, right? And so the moment we try to speed things up, we start running into these synchronization problems. Everybody see the essential synchronization problem here? This deposit account thing here is, and I'm going to use this word now, not atomic. Okay, and we're going to have to talk about atomicity as we go. But that lack of atomicity is potentially very problematic. Questions? So let's look at some ways we could parallelize this. So notice, by the way, that just adding parallelism doesn't necessarily make things faster. Because if I throw a bunch of threads at this, it could be that the overhead of switching the threads doesn't help me any. Because, you're just switch. You're spending all your time in the switch routine, which is pure overhead. So one way we could speed this up is an event-driven version, and we're not going to spend a lot of time on this, but I did want to mention it. So suppose we've only got one CPU, and we'd like to overlap I/O and computation. Then without threads, we're going to have to, we could write this in an event-driven style as follows. The bank server says, wait for the next event. If the event is, here's a request, start the request. Otherwise, if the event is account is available, continue the request. Otherwise, if the event count is stored, finish the request. Okay? Now stare at that a second. Can everybody kind of see how what I had earlier could map to this? What I've done is I've taken each of the things that could take time, like getting a request, starting the request by talking to the disk drive, storing the request. Each of those things are events. And so what happens is your incoming account request turns into a set of events. First, the request arrives, then it gets split into talk to the disk, then it gets split into each of these. And for every time I'm going to wait, I just sort of put the event back on the end of the queue, and I'm just pulling events off and processing them as fast as I can, and I get pretty much use the CPU at 100%, and we're good to go. Okay? And notice, by the way, I think the problems, of course, are things like what happens if you miss a blocking I/O step. So, for instance, if there's some event here that could take an arbitrary long time, you've just tied the whole bank up with that one event. So the only way that this works really well is if you have analyzed things well and you're willing to split them into little pieces and write your code in this way, which is a little bit contrary to the simple way of thinking of things, right? Okay. Does anybody know what is almost always written in an event-driven style? You use it every day. Yeah, graphical interfaces, exactly. So notice, every time you've got windowing systems and you move the mouse, There's a mouse movement events. There are things entering windows, exiting windows. There's keyboard requests. Inside of every operating system that has a windowing system into it is in a big event loop that just says, grab the next event, figure out which window it's for, send it to that window, grab the next event, and there's this huge loop. Okay, Microsoft Windows works that way, X Windows works that way. Pretty much every windowing system you're going to encounter is divided up like this. Yeah, question? Nope, you could easily do this at the user level. You could do this in a program that's running above the operating system. The operating system can do this. This event-driven style is a very common paradigm for programming. We're not going to talk any more about it in this class, but it is good to be aware of it because there are some things that are best done in an event-driven style. Okay? And a lot of things that are done in an event-driven style. If you want to, you could come talk to me afterwards or at office hours or something. We can talk about a lot more. But can threads make this easier? And I think the answer is clearly going to be yes. So threads give us this ability to overlap I/O and computation without sort of doing this complicated deconstruction. And you just give one thread per request, and the request proceeds to completion and blocking is required. So if every ATM request had a thread, then the fact that we're going to go through this deposit operation and there's a separate thread for you and it gets the account and that may use disk I/O and go to sleep and then it wakes up and then you do the sum and then you store back. This will be reasonably well optimized because if you have a lot of threads, most of them will be waiting for the disk, but some of them will be computing and you get full overlap and it's just easy to think about. One thread per request. Okay, now if we're worried about overhead, we go to thread pool or something, but for now let's just put thread pools to the back of your mind. Is everybody with me? So this is an alternative to the event-driven style. And this is, how many people think this is much easier to think about? Okay. How many people think event-driven is more easy to think about? Okay. How many people are not sure? Okay. So, unfortunately, here's where we get into our synchronization. So, by the way, threads are good for this example, perhaps. But now, here's our essential problem, right? And I'm showing this as if these are instructions, which is fine for now. But notice that thread 1 from your bank account and thread 2 from, both of these say are from your bank account, but this one is your parents putting in money, and this one is you putting in money, or vice versa. You see this problem is that we can load from the balance, these load from the balance, so now these two threads think the balance is identical. And this guy goes ahead, adds some money to it, and then stores the result back, and this one, meanwhile, adds some money to it and stores the result back. And which result wins? Last one, right? So thread 1. Okay, so I guess if thread 1 is your parents and they're putting in a lot more money than you are, that's better than it would be otherwise, but it's still not very desirable, right? How do we fix this? Okay, implement a lock. And we'll get to locks in a moment, but what's the essential problem here? Good, lock is right, but what's the essential problem? Yes? Yeah, the interleaving. So what we really want to do is we want to chunk up groups of 3 instructions so that they can't be broken up. Okay, and we can do that in lots of ways. We can do it with a lock. That's a simple way to do it, but there's going to be a lot of other ways we can do this. But essentially, we want those 3 instructions to be atomic, which means they can't be split up. And that's going to be how we fix this problem. Okay, does everybody understand the problem? Now, I want to show you a few more. So remember, what does it mean? We said this before, to run 2 threads concurrently. And we saw this sort of multiprocessing as things are running completely in parallel. Multiprogramming is they're split up in different ways. They could be interleaved where they all run for a while and then the next one runs for a while and so on. This is the evil scheduler view that you should keep in mind at all times, which is basically that if there is a way for the scheduler to cause your program to behave incorrectly, it will do it. Okay? And what could we do with this? Well, we need to recognize off the bat that there is shared state here, namely the account balance, and we've got to be very careful how we control entry into the shared state. Okay, and that's part of understanding the problem. Now, so the problem here is at the very lowest level, and most of the time threads are working on separate data, so it doesn't matter. So for instance, if we had thread A says x equal 1 and thread B says y equals 2, does it matter what order these are run in? No, right? The data is different. Here is kind of interesting though, right? So initially y is 12. What happens with the result of thread A and thread B? What are the possible values of x, for instance? Yeah, everybody's working through, well, we could interleave it this way or this way, right? By the way, you can see an obvious midterm question, right? I mean, hopefully. So, does everybody see that there are many possible solutions here? And you could say, well, you know, what happens is suppose that thread A runs to completion, and so x is 1, and then x equals y plus 1, but y was initially 12, so x ends up being 13, and then thread B runs. Or, you know, thread B runs to completion, so we start y equals 2, and then, you know, y equals y times 2, which is 4, and then we run thread A, and we could get a 5 out of it. Everybody see how you can come up with all these different interleavings? And, you know, what are the possible values of x here? It's a trick question, see if you're awake. What are the possible values of x here? 1 or 2? Okay. What about 3? Okay, why did nobody say 3? Pull out your binary. Use your binary, use your words, right? 1 is 0, 1 in binary, and 2 is 1, 0 in binary. And what happens if the bits are non-deterministically stored into the word so that you get the 1 in the 2's position from thread B and the 1 in the 1's position from thread A, and together they give you 3. Okay, yeah, so some reason you guys are rejecting this. You probably didn't think through it, but tell me a good reason to reject this.
Well, it's under the assumption that when you're doing it right, you'll clear whatever is there before you write.
Okay.
That's a good one, because obviously nothing will work.
Okay, so the essential assumption you're making is that loads and stores are atomic. Oh, we just used the new word, right? So, interesting, right? So you're going under the assumption that loads and stores are atomic, and therefore we're not going to get 3 out of this. But there are certain serial processors where you might not have that as a result. And in particular, there are a lot of 32-bit processors that when you're working on 64-bit floating point, you have to be very careful when you store the floating point out, because that becomes 2 stores, and those are not necessarily atomic. Okay. Don't let that keep you up at night, though. Okay. So what's an atomic operation? Okay, an atomic operation, we need to basically know what the underlying indivisible operations are. And so an atomic operation is an operation that always runs to completion or not at all. It's indivisible, cannot be stopped in the middle, cannot be modified by somebody else in the middle, and it becomes a fundamental building block for us. And so we just said, for starters, we're going to assume that loads and stores are atomic. Okay, that's going to be our essential first assumption. And the question that's kind of interesting is, how far can we get with that? Okay, can we do everything we need with atomic load and store? And on most machines, basically, memory references are atomic, so we're good to go. Many instructions, however, aren't. So I just mentioned the double precision floating point. There were instructions in a lot of architectures to do an array copy or a string copy. Those are also not atomic. Okay, so you've got to be careful when you start looking at the much more extended operations. Okay, is everybody with me on what an atomic operation is? It's a grouping that's indivisible. And clearly in our bank account example, we wanted that deposit function to be atomic, because the fact that it wasn't atomic caused us all sorts of problems. Okay? Now, so what are our correctness requirements here? So threaded programs have to work for all interleavings, have thread sequences, and cooperating threads are inherently non-deterministic and non-reproducible, and they're very hard to debug unless you design them correctly up front. And I wanted to give you a couple of examples. So I put up last time, and I eventually moved it to this time, some readings which, are kind of interesting and sobering. So one of them is the first, certainly the Therac 25 example is very sobering. So the Therac 25 was a miniature particle accelerator for doing radiation therapy. Okay, it's one of these, you go in, you've got cancer, and they want to direct radiation at very specific parts of your body to try to help cure you. And when you go into, to get these kind of treatments, you assume the machine is working. Now, radiation's never safe, but, you go in, you assume that the dosage is the right one for your treatment, right? Unfortunately, the Therac 25 was one of the first systems that was designed where all of the interlocks were in software. And furthermore, it had actually two types of dosage. It could either give you X-rays or it could give you electron dosage. And there was a table that would rotate on to put various blocks and prisms and other things in the path of the beam to make sure you got the right dosage. And that was all 100% under software control. Okay? And it turned out over the course of several years that several patients ended up getting badly burned because the software was buggy. Okay? Several people died. Other people got very serious injuries. And when analysis went back, what they found was there was a series of race conditions in shared variables in the software that caused the table to not rotate in the right way and patients to get, sometimes 1,000 times the radiation dose they were supposed to. Okay, and this was in a supposed system that had interlocks that was never supposed to fail. Okay, and here is one of my favorite really bad things. They determined that the data entry speed during editing was the key factor in producing the error condition. If the prescription data was edited at a fast pace, the overdose occurred. It turned out that the person giving you the radiation therapy was sitting there at a console. If they knew what they were doing, they would basically very quickly enter a bunch of stuff, go up, edit, put it back in. And the fact that they were fast at their job caused this overdose because there was an interlock condition that was poorly designed, and it basically crashed the system pretty much or caused it to do the wrong thing. So if you think that a synchronization bug is not potentially fatal, this is a good counterexample. Okay? Now, another less serious example was the original shuttle launch actually got aborted 20 minutes before the scheduled launch, and partly this was the fact that the shuttle was designed with so much redundancy. It actually had 5 computers, 4 of which worked together with a voting system to see that they were all doing the right thing, and then a 5th one which was busy checking the 4 computers. And so basically the 4 computers checked each other, the 5th one checked the 4 computers, and hopefully nothing would ever fail there. Okay? And it turned out that what happened, and by the way, they did something called inversion programming, which meant that this was written by a completely different team than this, so they're really checking everything. And it turned out that what happened was the countdown was aborted because it said, oh, there's an error, we've got to stop. And what was really going on was there was a race condition, and there was a 1 in 1/67th chance that the pass system was out of sync one cycle with the BFS system, and the bug was basically due to last-minute modifications in the initialization code, which nobody caught through simulation. It caused an abort, which cost zillions of dollars to do. And it was basically the fact that there was a timer queue that wasn't quite empty at the expected time, and the net result was these 2 things didn't actually match, and it aborted the flight.
But
so,
the system did its job, right?
Well, you know what? The system, in this case, the system did its job, but cost a lot of money. I suspect somebody got fired in this. I could be wrong. But, this is a much better scenario than the first one, right? But the bug was not found during simulation. This was only found afterwards when they knew what they were looking for. So, interesting. Okay. All right, so finally, let's do some, give you guys a break here and do some administrivia. So, don't forget the new section. We have a brand spanking new section Thursday, 12 to 1, 320 Soda Hall. And I want to point out, you've seen this posting, but you need to know your TA. There are those of you that, for whatever reason, are happily increasing the load of our couple of TAs that have 50 people in the class. And this is not a good way to get to know your TA. So I suggest that you check out the brand spanking new Thursday section, 12 to 1, which only has a few people in it. So that's a great way to learn your TA, okay? I wanted to apologize a little bit about homework 1. It got a little harder than we expected. How many people thought homework 1 got a little harder than we expected? Okay, so it's due next Monday, as you all know. The other thing is that I think the problems with the autograder have been fixed. For those of you that ran into that, we apologize as well. But hopefully, homework 1 is well on its way to being doable, finished. The other thing is the checkpoints for the labs have been moved forward 2 days. There's a couple of reasons for this. We looked more carefully at my schedule of things that I was teaching you about. And, okay, let's settle down, folks. And basically, as a result, we figured out that we would make sure that you would actually hear things a little bit earlier than you needed to put them in your checkpoints, which is good. And also would give you one extra section day. All right, you can take a look. I think the schedule has been updated or will be soon. Question? Nope. And no class on Monday. Yay, okay. Although homework 1 is due on Monday, but you could do homework 1 early, and then you could take Monday entirely off. Any questions?
But it's due like Monday at like 11:59, right? Or like any time on Earth or whatever it was.
Yeah. We actually just didn't. Did we decide we like AOE better than 11:59 p.m.? Okay, we got a lot of vigorous no's. How many people would have the presence of mind and control not to turn it in after midnight if it were due AOE? See, that's the reason for not doing it AOE, because most of you would just keep working on it when what you should really do is turn it in and go have a beer or something. No, I didn't say that. You should really turn it in and go have dinner with your family. All right, 11:59 on Monday, unless I hear significant request otherwise. 11:59 on various deadlines, yes. Okay. Okay, so any questions on the administrivia? Okay, we're a little bit behind today, but that's okay. So I wanted to give you one last example of motivation, then we're going to talk about ways of dealing with this. So suppose you have 2 threads, A and B, and they want to compete with each other. One tries to increment a shared counter, the other one tries to decrement it. Okay? Here's the code. Okay, so first of all, if you write this code and you're in a company, you're probably going to get fired. Okay? All right. So what's wrong with this code? What was that? Yeah, who knows what it's going to do, right? Is A going to win? Is B going to win? I'm going to posit that C is going to win. Okay, the problem is this is uncontrolled, and it's much worse than you think, by the way. So if we assume that memory loads and stores are atomic, but incrementing and decrementing is not atomic, then we got a big problem here, because it's not even the case that whenever you execute I equals I plus 1 or I equals I minus 1, that you actually end up increasing or decreasing I, because you can interleave different thread instructions, okay? Because I equal I plus 1 is not an atomic operation. Okay? So who wins could be either. Is it guaranteed that somebody wins? All right, there's why not? Well, you could print where A, B wins. No, the problem here is you could just keep somebody up incrementing, somebody decrementing. Maybe you just they stay in balance and you're stuck forever. That's another option. If both threads have their same CPU and they're running at the same speed, is it guaranteed that it goes on forever? Hard to say, right? Timing weirdnesses might run into play. Okay? So this is just bad code. So here let's do the inner loop here. Ready? Dun dun dun. So, looks like thread A is off to a good start. Then thread B is off to a good. Oh wait, A is now going along. Oh no, B is going along. Oh, A stores, B stores. Okay. So we're watching this and we're off. B says better go fast. A goes ahead, writes 1. B goes ahead and writes -1. A says what? I could have sworn I put a 1 there, and we ended up with -1. Right. So this is a good example where this is just bad code. Okay. Could this happen on a uniprocessor like this? So uniprocessor means one core. Less likely, right? Because we're going to... How long do we want to allow a thread to run before we switch it? Okay, yeah. So somewhere in the few milliseconds range, 10 milliseconds maybe. This is switching every instruction, right? So this is an unlikely a schedule for the scheduler to come up with, but who knows? Remember, the scheduler will do the most malicious thing it can, is the way you got to think about it. Okay. Any questions on this example? Have I beaten to death why this is a problem? You guys are with me? Okay. So, let's talk about how do we start fixing things. So, good thing about operating systems is the analogy between OS and life is closer than you might think sometimes. So, here's the too much milk motivation. This is for all of you that live with somebody else. Okay? So people need to cooperate, and so the trick is make sure that you're never out of milk in the refrigerator. So how does this work? So 3 o'clock, Frank comes home, he looks in the fridge, it's out of milk. He, being a good roommate, goes off to the store to get some milk. Meanwhile, George comes home at 3:10, he's on Berkeley time, and he looks in the fridge and they're out of milk. And so George, also being a good roommate, goes off. And meanwhile, he's walking to the store while we're buying milk. And then Frank comes home. Did I say Frank? Yes. Puts the milk away. George arrives at the store, buys milk, comes home, and now we've got too much milk. Okay? So, what's wrong here? Now, maybe you should have bought orange juice instead, right? But there's clearly a lack of synchronization here in the checking the condition on the milk and the decision to go out to get milk, right? So let's see if we can fix this in various ways. So what could we do to fix this? Yes?
You can create a lock on the refrigerator. So basically, when you see that there's no milk, super glue the door of the fridge shut. So
Surprisingly, that's going to be my first solution. So let's make sure we've got some actual answers here. So synchronization is using atomic operations to ensure cooperation between threads. Okay, there's a nice clean answer to what the synchronization is. For now, only loads and stores are atomic, and we're going to show that it's really hard to make synchronization when you only have atomic loads and stores. That's my next goal here, okay? So the only thing we've got is atomic loads and stores. Mutual exclusion basically ensures that only one thread does a particular thing at a time. Okay, so one thread's going to exclude the other thread. And then a critical section is a piece of code that only one thread can execute at once. So when we write code, we're going to want to have critical sections. Remember, that was our deposit method earlier, We're going to want to have critical sections where only one thread's allowed in at a time. Okay, everybody with me on these three definitions? Okay, and critical sections and mutual exclusion are kind of duals of each other. They describe the same thing. So a lock prevents somebody from doing something. So you lock before entering a critical section and before accessing shared data. You unlock when leaving. Okay, so this seems pretty simple. And you wait if locked. So the important idea I mentioned earlier, which we're going to say again, is all synchronization involves waiting. Okay, the way you synchronize is you make somebody wait to avoid confusion. Everybody with me on that? Simple. Now, for example, let's fix the milk problem by putting a key on the refrigerator. Lock it, take the key if you're going to buy the milk. Okay? And unfortunately, this fixes a bit too much because the roommate really only wanted orange juice. And now they can't even get their orange juice. All right? So somehow this lock seems a little bit too coarse-grained a solution, and you piss off your roommate. All right? So we don't even know how to make a lock yet, surprisingly. So let's see what we can do. What are our correctness properties? We need to be very careful about the correctness of concurrent programs. We've said that before. So here, we want to write down our behavior first and then try to write code for it. And the impulse that everybody is going to have is you start writing code first and you figure out what you intended to write later. Okay, don't do that. Okay, so instead, let's think first and then code. So what are the correctness properties for the too much milk problem? Number one, what? Yes? Don't end up with too much milk. Okay, what else? End up with milk. Okay, those seem like pretty good ones, right? Never more than one person buys. Somebody buys. Good. Okay, you guys are on it today. Good. So now we want to restrict ourselves to only using atomic load and store operations as building blocks. And here's our first solution. Ready? We're going to use a note. Okay? It's kind of a lock, right? I'm going to put a note on the refrigerator, hi, I'm out buying milk. And we're going to remove the note after we buy. It's kind of like an unlock. And if there's a note there, just wait. Everybody with me? Sound good? Now, unfortunately, computers are not very clever. And so if a computer tries to do this, we kind of run into this. If no milk, and if there's no note, leave a note, buy some milk, remove the note, poof. Good? Does that seem like the solution you'd come up with? What's the result? What was that? Well, you could end up with two people trying to put notes on the fridge simultaneously. Yep. Why? Because both threads, and now remember we're talking about computers which are not quite as clever as your roommate, basically say, well, they both say if no milk, they both say if no note, and they get to this part of the code and they both leave a note, go off, buy milk, and remove the note. There's nothing to prevent us from this particular piece of code getting into that part of the code. So even though we intended the leave note, buy milk, remove note to be a critical section, it isn't. Okay? And we can, and the way to think about this, remember that evil scheduler is the first thread comes along and right at this point it context switches to the other thread, which goes through this, leaves the note, buys the milk, removes the note, and then when we switch back to that original thread, they leave a note, buy the milk, remove the note. Okay, so the evil scheduler struck again. Okay, and so this solution, unfortunately, actually makes the problem much worse because now it's intermittent, it's hard to debug, and you have to somehow figure out what circumstances it occurs under. And think about that for a moment. Those two threads have been perfectly scheduled, so the first one runs a couple of instructions, gets switched out, the second one runs, and then another one comes back. Okay, so this is actually much worse because it fails intermittently. Now, of course, if it's really milk, what happens is you just make a bunch of milkshakes every now and then, and you're probably okay. But if this is something more serious, maybe this is not a good idea. So, oops, hello. What happened here? Dun-dun. All right, so let's see what... So we could say that clearly the note is not quite blocking enough. So let's put another note. Okay, let's try to put the note first. Leave note, if no milk, if no note, leave note, buy milk, remove note. So that's an extra little leave note in there. This is what happens. It's 4 in the morning, not quite AOE, and you're writing some code and you say, well, clearly it didn't block enough. I'm going to leave an extra block up there. What happens? Yeah, you could block yourself. Or essentially, you don't actually block yourself. What happens is you leave the note, you get into here and you say, oh, if no note, okay, don't do any of that, remove the note. So you never buy any milk at all. Okay, so this apparently good solution, you buy no milk. And what happens? Well, with a human, probably nothing bad, but in fact, with a computer, nobody ever buys milk. Okay? All right, here's solution number 2. Let's label the notes. Maybe the fact that we only had one note is a problem. All right, so algorithm looks like this. Thread A leaves note A, thread B leaves note B. And notice that thread A says if no note B, if no milk, buy milk, remove note A, and so on and so forth. What happens here? Yeah.
They both leave notes in the first step and check each other.
That's right. They both leave notes. Why? Because maybe they get switched at exactly the wrong time. They check each other and nobody buys any milk. Okay? Does everybody see that problem? You starting to see how to think about these? They're challenging, right? It's sort of, oh my gosh, does this work? No, it's possible for neither thread to buy milk. Okay, so context switches at exactly the wrong time, lead each to think that the other one's doing something. And it's really insidious because it's extremely unlikely that this is ever going to happen that way, but it will, of course, at the wrong time. And there's a bunch of... there's some evidence that there's a bunch of this in various operating systems where people didn't quite get it down right, and you get these things that fail, once every blue moon, and nobody really knows how to reproduce it even. Okay? I'm not getting milk. You're getting milk. Okay. This is a type of starvation. Any questions on this problem? So what the heck do we do? Yes? Lock the note. Oh boy, lock the lock. There's some sort of straitjacket and underwater breathing involved here, right? So this is a problem. Can anybody think of a way to solve this? We're actually almost there. Yeah. Oh, okay, we're not quite there yet. We only have atomic load and store, but good idea. Good idea. Yeah. Yeah, so form of busy waiting. So here's a solution. Stare at that for a second. Thread A leaves a note and says, as long as B has a note, wait. And then once B doesn't have a note, check for the milk, buy it if you need to, remove your note. And B, it turns out, has something much simpler, leaves a note, says if A doesn't have a note, and if there's no milk, buy milk, otherwise renew the note. Does this work? How many people think this works? How many people think this doesn't work? How many people just don't know? How many of you are sleeping? Nope. So believe it or not, this actually works. Okay, yes, you can actually go through and figure this out, and there's ways of doing this. You can say sort of at this X point, if there's no B node at this point, it's very safe for A to buy because you've protected by saying you've got a note, and if B doesn't have a note, then you know they're not in this code, and so you can safely buy it. And vice versa, once B leaves a note, you know that A is not going to go check the milk until B has removed their note. Okay, so this works. Okay, but what happens if you have 12 threads? Now what? You run out of, you have a lot of roommates. It's a fraternity. I don't know. This is really not a very nice solution because it's very asymmetrical. It turns out there is an arbitrary way to make this work, and you can do this, but this is not code you want to write. Correct? How many people do not want to try to figure this out for 3 or 4 or 5 threads, right? This is just bad. It works, just not very desirable. Now, okay, so our section basically it's a way of looking at protecting this critical section. And solution number 3 works, but it's very unsatisfactory. It's complicated. A's code is different from B's. And the other really kind of insidious thing that we've introduced in here is that while A is waiting, it's busy spinning. So we're actually put busy waiting into this solution to make it work, and that's never a good idea because it's just wasting CPU time. Okay? So what we'd really like is a better implementation of an actual lock where we have something like this, lock.acquire, lock.release, where lock.acquire waits until the lock is free and then grabs it, and lock.release unlocks it and wakes up anybody who happens to be waiting. Okay, and if we have that, we have to make sure these are fully atomic. I haven't told you how to build these. But if we had a lock.acquire and a lock.release, then suddenly we could build this way. This is our code for however many roommates we happen to have. Milk lock.acquire, if no milk by milk, milk lock.release. The end of story. Isn't this a much nicer abstraction? Now, buried in here, unfortunately, is the following thing. How does acquire work? How does release work? Okay, we have to figure those things out. The thing about acquire is what you don't want to have happen is that acquire busy spins. Okay, you'd like acquire to do something more intelligent, like maybe put the thread asleep so it's not wasting cycles, and then on release wakes up the threads who might have been trying to acquire. So that all gets into our question of how are locks actually implemented. Okay? Questions? Isn't this it's always nice to have symmetrical code, do you not think? And once again, any of the code between acquire and release are called critical sections. And of course, you can make this even simpler. Suppose you're out of you're out of ice cream instead of milk. Skip the test since you always need more ice cream, of course. So that would be my solution. But okay. Any questions on the lock, acquire, and release? Yeah.
But I mean, there are also problems. For example, if there are multiple items instead of just milk, and say like you have the milk lock and you're waiting for the broccoli lock, and the other guy has the broccoli lock, he's waiting for the milk lock, and you're both screwed.
The clear answer to that is don't eat broccoli. Yeah. So there's a lot of complexities when you generalize the solution, but let's see if we can solve this one first, okay? All right, should we take a brief break?
Yes.
Okay, 3 minutes. Stand up, say hello to everybody. rush you guys back. I want to try to get through a couple of things today. Help out with the projects. So, bottom line here is if we can figure out how to do a good implementation of a lock, we might be well on the way to being able to support critical sections, which make us be able to at least design synchronization operations. Okay, so where are we going with synchronization? At the hardware, there's a bunch of options for various things, and we're going to talk about some hardware things like test and set in a second, which let us then build all sorts of interesting synchronizing primitives like locks, but also like semaphores and monitors and various other types of higher level APIs. And then, of course, those let us build actual programs with threads in them. So down at this lowest level, we've been kind of stuck with the fact that our hardware only has atomic loads and stores, and that's really made that solution, the too much milk number 3 solution, very unsatisfying. Because the only thing we could trust was that loads and stores were atomic, and that was it. But let's see if we can, first what I want to do is I want to try to increase our set of hardware operations a bit to help with this, and then we're going to talk a little bit more about how to build locks and some other things like semaphores. And so I want to try to do some of this before the end of the lecture. So the lock basically prevents somebody from doing something. To be particularly clear, the idea is you lock before entering a critical section and before accessing shared data, and you unlock afterwards, and you wait if you go to grab it and it's already locked. Okay, so that's our important idea here, is that all synchronization involves waiting. And you really want to make sure that if you have to wait, you want to sleep. Okay? Wait till the end of the class. That's going to be an important idea as well, because when you design synchronization primitives, you're going to not want a busy wait. And we'll talk more about this as we go. So atomic load store is fine, I guess, but it really got us this ridiculous milk number 3 solution. And so how about a hardware lock instruction? Here, we'll just lock. Does that work? It's got the whole thing in it. It checks to see whether somebody's got it. If it doesn't, it puts you to sleep, all in one hardware instruction. Why not? Do we need something that complicated in hardware? How many people think we should try to put it all into one instruction? Okay, we got one taker. Okay, now I will say that if you look at this, that one instruction is a mess, okay, because it's dependent on the operating system. And they try to do this in some processors. You can look up the Intel 432. This is something you've never heard of, and most people haven't because it's sort of buried in the dustbin of history. But the issue there is really that some of these things like putting threads to sleep, that's an operating system concept, not a hardware concept. And by trying to jam all of that stuff into the lock instruction, then, you know, we're limited in what operating systems we can design, and we're limited in all sorts of stuff. So we don't want to go that far. We'd like to say what little bit of hardware beyond just atomic load and store give us enough to build a good lock. And let's see, what about interrupt disable? Right? We could do that. So recall that the dispatcher gets control in one of two ways. Either the thread does something to relinquish the CPU, but we're not talking about that right now because the threads are running, or interrupts, like a timer. So gee, why couldn't we just avoid context switching by setting an interrupt, running our critical section, re-enabling the interrupt. Disable interrupt, critical section, re-enable interrupt. Does that work for a lock? What? Yeah.
If someone's critical section, they basically
Yeah, there's a little bit of a problem with that because you turn off interrupts and you're busy computing the last digit of pi. Now what? Okay, no interrupts ever happen again. And so here's our implementation of locks. Lock acquire is disable interrupt, lock release is enable. Seems attractive until you start thinking about it a little bit. And some problems are you can't let the user ever do that because we never want to let a user disable interrupts. because they can crash the system. And real-time system, you don't know how long that critical section is going to take, and interrupts need to go off with the timer, otherwise we can't keep real time. And what happens with I.O. and other important events like, oh, here's an interrupt that the reactor's about to melt down, and you're busy computing pi with interrupts disabled. Okay? Probably a bad thing. So this seems attractive, but probably isn't what we want. Everybody with me? So can we do something else? So what if we maintain a lock variable and do something a little bit tricky like this? So the lock itself is going to be this value variable, and what acquire looks like is this. It disables interrupts. It says if the value is busy, meaning somebody's got the lock, then we're going to put the thread on the wait queue to go to sleep. Otherwise, we set the value to be busy because we've acquired the lock, we re-enable interrupts, and we return. Now, notice that I've only disabled and re-enabled interrupts briefly, just long enough to check the value of busy. So this is not holding interrupts disabled for a long period of time, just for a short period of time. The lock itself is that value thing. Okay. Now, how do we release? We disable interrupts again. We say if anybody's waiting, take them off the wait queue, put them back on the ready queue. Otherwise, and this means that some thread will keep the lock, and so we just leave it busy. Otherwise, we free it and re-enable interrupts, and we're good to go. And the justification for this kind of an implementation is, well, I don't disable interrupts very long. Yes? Well, what's nice about this is, so we're going to talk about deadlock later, but if you're ever waiting for multiple locks, you need to wait for them in a certain order, otherwise you can get deadlocks. So let's assume that you're doing the right thing there. This just works because for every lock, suppose I have thousands of locks, I just have thousands of integers, and every time I acquire, all I need to know is what I put the address of this particular lock into my acquire operation, and I can make it work that way. Now that totally doesn't solve the deadlock problem, which is, you programmed it badly, but we'll leave that out of the picture for a moment. Good question, though. Okay? So, why do we need to disable interrupts at all? And the idea is we've got to avoid this interrupting in here, because this is a critical section with respect to the implementation of the lock. Now, boy, talk about, who said a lock on a lock, right? This is a lock on the lock. Okay, but this is an implementation of a lock. And otherwise, two threads can get in there and think they both have the lock. And this is a critical section in the lock implementation. The user who uses it will have their own critical sections. Okay? Now, unlike the previous solution, the critical section is very short, so this is probably an okay use of interrupts. And the users of locks can take as long as they like in their own critical section because they hold value equal busy for an arbitrary amount of time, but they don't mess up the kernel. The kernel just disables interrupts, re-enables them, and can busy deal with the reactor melting down. Okay? Everybody with me? Questions? Yeah.
So what happens when the lock isn't available?
You mean like right here?
Yeah.
You put the thread on the wait queue, you go to sleep, and you exit. Now, if you look at this very closely, that's a very good question. Well, you put the thread in the wait queue, you go to sleep, but wait, interrupts are still disabled here. What am I going to do, right? Is that what you're asking?
Well, I guess I'm asking, how does it ever get back to acquiring the lock?
So the way it gets back is that somebody wakes us up with the lock, and then we exit this sleep with the lock and go through the re-enable. So what I haven't showed you here is what happens. We go to sleep, we get put on a wait queue. Later, somebody wakes us up with the lock, and we continue. Okay? But the problem that we haven't solved here is this one, which is a little funny. I go to sleep with interrupts disabled. Now what? Now interrupts are disabled, and I'm sleeping, and I'm not turning them back on. Right? So that looks like a problem with this particular implementation. And if you look carefully, you could sort of say, well, I could re-enable interrupts here before I go to sleep. Yeah, question.
When interrupts are disabled, that's only for that thread that they're disabled?
No, interrupts are disabled for the whole machine. Okay, so we got to be darn careful. And actually, when you have a multi-core, you might disable them for just one processor. But for now, let's leave that out of the picture. But if I re-enable them there, the problem is that there could be an interrupt. Somebody else, a thread could take control and get in here and release the lock just as I went on the wait queue to go to sleep. All right, so this seems bad. I could try to re-enable interrupts here, but that would mean that I put myself on the wait queue and somebody, again, wakes me up just before I go to sleep. I could put them there. Well, I can't put them there because I go to sleep, so I don't ever get there. So this, how do I re-enable interrupts, seems like a little bit of a flaw with this particular solution. Okay? Now, in the scheduler, basically, interrupts are typically disabled, and so you can deal with the sleep there, and so this is what really happens. Oops. Okay? We disable the interrupts, we go to sleep, we context switch to somebody else who in the process of waking up re-enables interrupts and goes through. Okay? So this is actually how we handle that particular little issue in the scheduler. Okay, now, I want to end up with at least one thing here. The problems with all the previous solutions are the following. So because it still disables and re-enables interrupts, none of these locked solutions work at user level. So basically, I've not given you anything that works at user level yet. Could do it in the kernel. The other problem is it doesn't work on a multiprocessor because typically you disable, or multi-core, because you disable interrupts on one core, but the other one's still running. So that also doesn't seem very desirable. And so an alternative is what are called atomic instruction sequences. And these instructions basically read a value from memory and write a new value atomically. The hardware itself is responsible for implementing this correctly. So this is raising our atomic sequence from just load and store to something a little more complicated like test and set. Okay, and unlike disabling interrupts, you can use this on a multiprocessor, and so here's some good examples. This is test and set, and this is just pseudocode of what the hardware does, but the hardware gets the value out of the address and sets the value to 1 and returns what was there before it set it to 1. That's called test and set. Read it first, test it, set it, okay? There's also things like swap, where we swap the value that is in memory with a value in register. There's compare and swap, where we take the value out of memory where the lock is, we compare it with one register, and if they're still equal, we store a second register back to the address. And then there's even something called load link store conditional, where we do this, where we load the address, we go ahead and do anything we want arbitrarily and try to store it back. And if somebody has gotten into the middle of this and screwed this up, then we get a null solution and have to keep retrying until we actually get an atomic sequence out of it. Now, I'm going to go into more depth on these next time. But let's briefly see what we can do with test and set. I want to leave that with you guys. This is another slightly flawed but very simple solution where acquire says while test and set, and release set of value, and release says set value to 0. Okay, so why does this work as a version of acquire and release? Acquire works because if value starts at 0, when I go to acquire, if I'm the first one to acquire the lock, I get a 0 out and I store a 1 back right away atomically, and now I get a 0 comes back from test and set, I exit the while loop, I've acquired, and now I'm good to go. If I'm anybody else, they all try to run test and set, and what they get out of there is a 1, and they store a 1, and, they got a 1, and so they send here and they busy wait. Okay, only the first one through this sets value to 1, but gets back a value of 0. And then the way we release is I just store a 0 there, and the first thread that tries to test and set after that gets to get a 0 back and store a 1, and now they've got the lock. Okay? Now, there's a lot of problems with this, right? Does everybody see why this works? This actually does work. Any questions about why this works? Notice that atomically, I both grab the value at the lock and store a 1. That's the atomic operation. Notice that that's more complicated than a load or a store. Okay? But it lets me build a lock, and this works. Okay? The problem here, of course, is busy waiting. That's one big problem, because I spin while I'm waiting. The second is that there's chaos on here, that I store a 0, and suddenly every thread tries testing and setting right away again. Okay, so it's not a very good controlled way of giving control. And so we'll leave you with this. The problem with busy waiting, so positives for this solution is the machine can receive interrupts because we never disable them. The user code can use it. Works on a multiprocessor. Negatives are it's very efficient because it's busy waiting. The waiting thread may take cycles away from thread holding the lock. Why is that? Well, because there's a thread that's just spinning there, and the thread that's got the lock that needs to do the stuff it needs to do before storing a 0 doesn't get to go forward because there's a thread that's busy spinning. That's the essential problem with busy waiting. The one who's trying to get the lock is wasting cycles when the one who's got the lock doesn't get the cycles. Okay? And there's also a priority inversion problem here because the busy waiting thread, if it has higher priority than the one holding the lock, the busy waiting thread is going to busy wait forever, and the one that has the lock will never release it. Okay? And priority inversion problem was exactly what killed the original Martian rover. I'll tell you a little bit about that next time. But for semaphores and monitors, which we'll talk about later, we have a better solution where waiting thread can wait for an arbitrary time. All right, so let's, in conclusion, the important concept for today was atomic operations, an operation that runs to completion or not at all. And these are the primitives on which to construct various things. We just discovered that test and set might be a better primitive to build other locks. We talked about hardware atomicity primitives, such as disabling of interrupts and so on, test and set. And we're showing several constructions of locks, and what we've got for next time, which I didn't quite get to this time, and which you're going to get to in section, for the first time, unfortunately, is we're going to talk about semaphores and monitors and condition variables in depth next time, which are better alternatives to locks when you want to try to build more complicated things. So have a great weekend. Have a great holiday. Do go to section. In fact, everybody, no, I take that back. A good subset of you, like 25 of you, ought to go to that Thursday section, 12 to 1 in 320.